Okay. We start with our third module where we examine different actions and a combination of these actions. The primary purpose of the third module is to examine behavior of masonry in a detailed manner and be able to arrive at a closed form solution, closed form analytical expression for masonry under different actions and combinations of actions. Now that becomes important because we are then able to establish the strength under different actions of different sizes of masonry components. Maybe you are interested in looking at slender walls, squat walls, beams, columns and so on, starting with compression, concentric compression, eccentric compression, bending, out of plane bending, and then finally in plane bending or shear acting on a masonry wall. And then of course we are interested in understanding how they interact with each other, axial load with moment, axial force with shear force, and have our failure surfaces under these actions ready and understood as far as the behavior of masonry is concerned. This becomes the analytical basis for design, right. So the next module, which will deal with design, is going to be really feeding into the behavior of masonry under different actions. So I begin with the mechanical behavior, the mechanics of masonry in compression. This is something we have already seen quite carefully, particularly the coaction between the unit and the mortar. However, the intention is, if you were if you had with you the strengths of the constituents and the properties of the constituents, the unit and the mortar, will you be able to estimate the compressive strength of masonry? It is not often that you will be able to carry out an experiment in the laboratory and say this is the failure strength of the masonry that I am going to be working with. You need to have an understanding analytically how this is performing, and the unit strength and the mortar strength is something that you can establish quite easily even in practical situations. So with that knowledge, is it possible to be able to arrive at, for a complex behavior as we have seen because of the coaction, what is the failure strength of masonry itself in compression? Okay. So we are examining in today's class we are going to be examining uniaxial compression only. Concentric, we have still not we wouldn't be going into strain gradients due to eccentricities of the compression, and we are looking at the strength in compression of the masonry. It is not the strength of a wall, we are not bringing in the slenderness of the masonry wall where second order effects can come into the picture. So we are still examining the masonry as a material under compression. So we have studied this carefully, and we discussed that the strength of the masonry is going to lie somewhere between the strength of the unit and the strength of the mortar, and this is because of the coaction that occurs between the two, between the unit and the mortar. The unit is going to be the stronger of the two, but the more brittle of the two, less deformable of the two. The mortar is more deformable, weaker in strength, but what you get as the combination of the two, because of the bond that is established between the two constituents, is something in between. And we have also examined how the state of stress in the multiaxial state of stress in the unit characterized by the uniaxial compression and the bilateral tension forms, and how the triaxial state of compression forms in the mortar because of the confinement offered by the unit itself. So let us keep that in mind and use this as a basis for the formulations. So I am going to be examining the formulation under an assumption of linear elastic behavior of the unit and the mortar, which is of course not true. As you know, we are dealing with materials which have different strengths and can enter nonlinearity and elasticity quite early, and therefore we will examine a second theory which accounts for the inelastic behavior of both the motor and the unit in arriving at the failure strength of the masonry itself. So, to begin with the linear elastic theory, this is a well established theoretical framework. It comes from the work of Haller, Francis several decades ago. Assumption, the fundamental assumption here is the entire assembly is working in an elastic manner, right, and that is where the problem arises for us. Okay. So, we were talking about the Poisson's effect being fundamental in creating the states of multiaxial stress in the unit and the motor. So, if I were to examine the brick unit, just to get the notations familiarized, we are looking at the z axis, the stress acting in the vertical direction, uniaxial compression, the axial compression as sigma z, the bilateral tension in the brick unit in the two directions sigma bx and sigma by, whereas the multiaxial state of stress of compression in the unit in the motor sigma z as the axial compression, and the other two directions which are also in compression sigma jx and sigma jy. Here the subscript b is used to refer to the brick unit and j is referring to the joint itself. So, we have sigma z bx and by, sigma z jx and jy. So, in terms of the dimensions of the unit and the motor joint, we are looking at the thickness of the brick unit as Tb, the Tb here, and Tj as the thickness of the motor joint. Okay. Now, based on an understanding that under a state of triaxial stress, Poisson's effect comes into the picture. We can write down the deformation in the brick unit and the deformation in the motor with respect to the states of stress in the different directions. So, if you look at the deformation in the brick unit, we can write down the strain in the brick unit in the x direction. So, epsilon bx in terms of the triaxial state of stress, Eb here refers to the modulus of elasticity of the brick, sigma bx is the direct stress in the direction bx, nu b here is the Poisson's ratio of the brick unit, and the other two directions and the stress in the other two directions sigma z compression and sigma by. So, we are looking at the Poisson's effect with respect to the triaxial state of stress. Similarly, epsilon by is written down, we have the states of stress sigma by, which is going to be the direct contributor to epsilon by, and the Poisson's effect in the other two directions causing changes in the strain in the direction by. Similarly, we write down the deformation of the motor joint itself. Motor joint is in triaxial compression. So, you have epsilon jx, so the compressive strain in the joint in the x direction and the compressive strain in the joint in the y direction, where Ej is the modulus of elasticity of the motor joint. Again, the deformation, the strain caused by the stress which is in direct correlation to the direction. So, sigma jx and sigma jy for epsilon jx and epsilon jy, and the other two directions caused because of the Poisson's effect, and nu j here refers to the Poisson's ratio of the motor or the joint material itself. However, we know that a bond exists between the two materials, and therefore, there is compatibility of lateral deformations that will occur. There is going to be a compatibility of the strains, a compatibility of the lateral deformations because of the existence of the bond, which means that the strain in the x direction in the brick unit is going to be the same as the strain in the x direction in the mortar material as well. So, epsilon Bx should be equal to epsilon Jx and epsilon By should be equal to epsilon Jy. That is basically the lateral strains at the interface should be same as long as equilibrium is maintained. Till you do not have failure, this is acceptable, right. We also have to consider equilibrium of forces. So, if you are going to be looking at an equilibrium of internal forces in both the x and the y directions, the lateral directions, we can examine the thickness of the mortar joint, the thickness of the brick unit over which these stresses are acting, and write down the equilibrium in these two directions. Sigma Bx is alpha times sigma Jx. There should be an equilibrium of forces. So, sigma Bx is some factor times sigma Jx, and that factor is nothing but the ratio between the thicknesses of the joints, which is Tj by Tb. So, sigma Bx can be written as Tj by Tb into sigma Jx, and similarly sigma By can be written as Tj by Tb into sigma Jy. So, this is the basic set of assumptions that we are working with, and the force equilibrium and the compatibility among the compatibility of deformations is what is helping us write down this set of expressions. Okay. If we were to combine the previous set of expressions, the final output what we are interested in arriving at is, can we get an expression for the stress at which the masonry will fail under sigma z. Sigma z is the vertical compression. We want an expression for sigma z which is a function of the constituents, the modulus of elasticity of the brick, the modulus of elasticity of the mortar, the geometry of the unit and the mortar, particularly the joint thickness, and the Poisson's ratio of these materials. So, knowing the constituent materials and the constituent strengths, the tensile strength of the brick unit, the compressive strength of the mortar, will we be able to arrive at sigma z, or the failure value of sigma z itself. So, in the previous expression that we previous set of equations that we have looked at, you have seen alpha is representing the joint thickness ratio. Similarly, if we were to use beta as the ratio between the modulus of elasticity of the mortar material to the brick unit, we are writing down sigma Bx is equal to sigma By in terms of sigma z. So, it is a mere rearrangement of the previous set of expressions which are based on the deformation. Now, those were expressed in terms of the strains, we are writing them in terms of sigma Bx and sigma By, eliminating the different stresses in the unit and the mortar with aspects that we are able to measure and know, the geometry and the individual values of Poisson's ratio of the mortar, Poisson's ratio of the brick, and the moduli of elasticity of the two materials. So, you see that the expression that you see here basically eliminates the unknown states of stress. So, we have an expression of the local stress here, which is the tensile stress that the brick unit is subjected to, sigma Bx and sigma By. It is important to be able to write it in terms of that stress, because we know that the brick unit will fail in tension, right. So, we have an idea of the mechanism. Since the brick unit is expected to fail in tension, we now have an expression that relates the stress in the brick unit, the tensile stress in the brick unit, to this overall stress, the vertical compressive stress that you are actually applying and under which the prism is going to fail. This is a generic expression. We now need to be able to plug in strength values, and the reason why it is in this form is you already have the stress and tension of the brick unit, right. Sigma Bx and sigma By are actually tensile stresses, but we know that the brick unit is going to split it is going to split at its tensile strength. So, if I have an estimate of the tensile strength of the brick unit, I can plug it in here to be able to get an expression in sigma z. So, that is the way it is designed. So, you need a criterion for the failure of the brick unit. If you remember the graph that we had looked at, the figure that we had looked at in terms of the behavior, the stress path in the unit and the stress path in the motor, we will come to that in a moment. We were assuming, and it is a fairly reasonable assumption, that the failure plane in the brick unit under compression and tension is a straight line, right. So, that forms a criterion for us. You have a straight line interaction between the compressive strength of the unit and the tensile strength of the unit. That is a straight line failure plane. So, if FBC is the compressive strength of the unit, the uniaxial compressive strength of the unit, and FBT, so FBT is the uniaxial tensile strength of the unit. If you were to do a direct tension test and get the tensile strength of the unit, you do a uniaxial compression test, flatwise compression test on the brick unit, you get FBC. So, with FBC and FBT available, a straight line interaction between the compressive stress in the brick unit sigma z divided by FBC, which is the failure stress in compression, plus sigma t, which is the tensile stress in the unit, to the failure stress in the unit in tension, lambda FBC. Lambda FBC is nothing but where lambda is just the ratio between the tensile strength and the compressive strength. And it is only to make things a little simpler that we are looking at a ratio such as lambda here. We have discussed that the tensile strength of brick would be about 10% of the compressive strength. So, you could work with, if you do not have the exact value coming out of a direct tension test, you could still use this relationship between the tensile strength of the unit and the compressive strength of the unit itself. So, you have this straight line failure surface of the brick in tension compression, which is what we will feed into to be able to establish the criterion. So, if we now substitute in the expression, we have been using sigma bx and sigma by, which are nothing but tensile stresses in the unit. So, we have an expression here in sigma t. So, sigma bx and sigma by are being substituted by sigma t in the failure criterion, and rewriting in terms of sigma z, we get an expression for sigma z. Since we are now bringing in the failure strength in compression of the unit, the sigma z is going to be referring to the failure in compression of the masonry assembly itself. So, we have an expression now which is the failure strength of masonry under uniaxial concentric compression, where the parameters that you require are the Poisson's ratio of the unit, the Poisson's ratio of the motor, the modulus of elasticity of the unit, the modulus of elasticity of the motor. You have the term alpha, which is nothing but geometrical parameter, joint thickness versus the brick thickness, and finally beta, which we already have, and finally lambda, which is nothing but the ratio of the strengths FBT by FBC. So, this is an expression that is fairly good, but linear analysis is the basis, linear elastic analysis is the basis of this expression itself. So, the fundamental limitation of this theory, which is often referred to as the two people who propounded this initially, Haller-Francis theory, is the fact that we are assuming linear elastic behavior, and we know that the motor and the unit to an extent, much more the motor, is not going to behave in a linear elastic manner. And the problem of considering this sort of a basis for the behavior of the masonry composite is that, you remember this this picture where you have axial compression, which is the load that is being applied, the stress caused by the load, the compression load that is being applied against the lateral compression, lateral tension. The point is, the stress path in the unit is assumed to be linear, and then it hits the failure criterion that we have used, which is the straight line in compression and tension envelope for the unit. We are again assuming that the stress path in motor is the stress path of the motor in the prism is also linear elastic. We would not be able to explain how the unit and the motor fail together in reality. In reality, you expect a simultaneous occurrence of the tensile cracking in the unit and loss of confinement and the crushing failure of the motor. If you go by this theory, depending on what the motor strength and the unit strengths are, you will get a disparity between the points of failure. So, according to this theory, brick will fail, and then after some time you increase the load and then the motor will fail, which does not happen. There is a simultaneous failure of the two. So, I will stop here. We will come back and examine the same situation, but with motor strengths different from the unit strengths as shown here, and then examine how we go into a situation where inelastic behavior of the motor can give us a much better prediction of the mechanical behavior under compression. Thank you.